4:20. Everybody have a good long day here? Everybody ready for a nice talk on DNS, right, at 4:20 in the afternoon? Thanks everybody for making it out. And today's talk, call it Reprogramming the Programmer, and this is an experience journey through building a system and the evolution of that system, as well as hopefully there's a little bit of personal evolution that comes through in the message as well. So the agenda really is, we're going to give a little bit of background from the golden age of hip hop through 2015, the building, the few versions of the system that we built, and then just wrap it up with some lessons learned. So starting out, I had spent most of my career building software in Java and C#, about 16 years of that, and there's this characteristic of the systems that I built that became recurrent, and I refer to it as MOOP, which is maligned object-oriented programming. I was very careful not to say all object-oriented programming is bad, but maligned object-oriented programming, where I say any system characterized by lots of objects, imperative programming, side effects, mock objects, and wrapped around some kind of dependency injection framework. And so this was the typical of the system that I was starting to build. And these types of systems are hard to reason about. You almost have to download all the code to understand exactly what's going on. The systems become brittle over time, become difficult to extend in an error-free way. I actually did spend about a year in management because I was convinced that there was no path forward with programming for myself. People don't compile. I mentioned the other day that there's no Stack Overflow for people. So kind of made my way back into engineering after that. And within these types of systems, when you build a MOOP type system, is we like to throw a lot of patterns at these things. We have MVP, MV star, MVP, sorry, that's another buzzword, MVC, MV star, gang of 4 patterns, et cetera. And we like to think that we have this really awesome structure, and the data flows within our system are very obvious and very easy to extend. The more interfaces, the better. But it actually turns out that in reality, it's not quite as obvious. There's a lot of mutating of state going on. It's hard to track what's going on when in the system. And I tend to think that a lot of the cause for my headaches, at least several years ago, was due to dependency injection frameworks, in particular auto wiring. So how many people here have actually written code like that? Awesome. So let the record show that we are all guilty in this audience. That's 20 dependencies. I've seen as many as 40. And I like to say that no matter how many of those you have, there's always room for one more. Right? And so that's anytime you want to add behavior to a system, you always have a spot for it. And of course, the more dependencies that you have in your system, the more staging and mock objects and expectations that you have to build as well. And you can imagine when you want to add a parameter to a method or something like that, you have to go and update 30 or 40 unit tests and the expectations that you're staging with your mock objects. So in 2015, I had an opportunity to change things. Comcast runs a program called Summer of Code. It was a chance to build something from scratch so that I could avoid all the MOOP ugliness. And it was DNS as a service. So, what's DNS? This is the most interesting part of the talk. How many people hear DNS? Okay, we can commiserate later. So it is hierarchical and decentralized are the 2 keywords there. And the idea is that you have all of these records that are all over the internet. You need a way to manage them in a redundant way. And I like to think that, I like to think of DNS as a large, loosely coherent distributed KV map. And the idea with DNS is that zones are hierarchical. Each node in the hierarchy that you see here is its own DNS zone. So .NET is a DNS zone, Comcast.net is a DNS zone, sys.comcast.net is a DNS zone. And the idea is that these zones can live on separate DNS servers. That's how we get the distributed nature of DNS. And really all a DNS zone is a group of records. And so what is a DNS record? So a DNS record is how we name things and how we answer questions like, what is the IP address for scala.bythebay.io? And we see here an example of a DNS record. And just real quickly, the first part is often referred to as the FQDN, fully qualified domain name. It's the key in our key value map. The first part of that is the record name. The last part of that is your DNS zone name. We have this TTL, which tells you how long you're going to cache your browser, cache this record. If you do a dig and you get a lookup in 7200, it's 2 hours. So please don't ask your DNS engineering team like why your change isn't seen yet. It's likely cached somewhere. The record type's important because that says what's the type of data that's held. Like the A record is IPv6, and then of course we have, or IPv4, and then this is IPv6. All right, so the concepts are pretty easy. A zone is what we care about, and it's just a group of records. So that's the kind of the crux of DNS. So version 1 of the system, we had a short time to build it. The primary audience was we're going to support internal engineering teams in managing their DNS. We imagine that we might have 1,000 DNS zones, 100 records per zone. We assume records did not change all that much, and that we needed to audit all the change. It was important if somebody was to delete www.comcast.net, we know who did it. Okay. So going into version 1, the approach was let's use SCALA and Akka. I had actually already some experience with SCALA and Akka. The team that I rotated into the Summer of Code was already familiar with SCALA, Akka. I decided not to use Java, and so that we could build it MOOP free. So the design that we chose was event sourcing as the architecture pattern. And the nice thing about event sourcing is that there is no state that exists in a database. You have events that are stored in an event journal. And when an entity is loaded, then the events are basically replayed in order to generate current state. So what does that look like? So this is an example of event sourcing. When you have a command come in to add a record to a DNS zone, it's going to apply some changes to the back end. When that event is complete or that command is complete, we're going to persist the event into our journal, kind of like a write-ahead log. The important part here is state is updated in memory. That makes reads hella fast. You get like sub-millisecond resolution when you're doing queries against this event source system. And when you cold load an entity, really what you're doing is saying, hey, give me all the events since the beginning of time for this entity and just replay them in order back in order to generate current state. So that's the idea with event sourcing, and it really turns out that Akka is really well suited for event sourcing. It has it out of the box with Akka persistence. And the way that you go about and implement this is zone state is stuff in memory. It's just typical case classes. We made each DNS zone its own actor because that was the entity that we cared about. The persistence comes for free, and it turns out that there's other tools like Akka cluster sharding and Akka clustering that'll come into play as well. So in-memory state, what does this look like? It's just a case class. I have the list of all the changes that I can query. I have indexes that you don't see here. You have your record data and you have your zone metadata, and that's what you have to implement for your zone state, so to speak. The key for Akka persistence is you extend this, you get this trait called persistent actor. It provides the magic like persist, and that's how you save an event in your journal, right? It's a method that just comes out of the box. You don't have to worry about anything else as far as persisting your events. For the replay, when a DNS zone loads, you get this receive recover that you have. It's a callback, and it sends the events in, and then you just kind of regenerate your state. All right, so that's the Akka side of event sourcing. Akka clustering is one of the technologies that we use, and we use it for HA. So Akka clustering uses gossip underneath the covers in order to figure out who are all the nodes that are participating in this cluster. And then the other piece of Akka clustering that we employed was Akka cluster sharding. And what Akka cluster sharding does is it says, answers the question like, okay, I have this persistent zone thing, how do I make sure that it exists once in the cluster? And Akka cluster sharding is really part of all that. So in cluster sharding, a shard is really nothing more than a group of zones, zone actor instances, and the cluster sharding system just makes sure that your zone actor exists once within your Akka cluster. So for example, when you get a command that comes into the cluster sharding will just automatically make sure it forwards it onto the right zone actor, the zone actor that you care about. The last thing that we get with Akka clustering is high availability. So if one of the node fails, then the shards in that node that failed are automatically redistributed to the remaining nodes in the cluster. Cool. And That's our persistence layer. The nice thing about Akka persistence is that it has these plugins, and all you got to really do is pull in the right dependency and just configure it, and you're done. So to recap our event sourcing solution, we were able to go from 0 to prod in 3 months. The system was super simple. I mean, there's an AngularJS front end, not super simple, but the crux of the system was actually really, really easy, very, very little code. A shout out to the Akka community. You know, I was talking to a lot of people in the user groups for Akka during this time. Roland Kuhn I actually talked to in the user groups, and he was great. Akka does have a tool for everything out of the box. And the system really didn't have these characteristics of MOOP at least right now. Cool. So we were in production for about 3 months, and then the larger DNS organization at Comcast found out about what we're doing and said, hey, how about we use this for all of Comcast? And so the Comcast has one of the largest DNS footprints in the world. And what does that mean to our system? So instead of 1,000 DNS zones, we have millions of DNS zones. Instead of 100 records in a zone, we have our largest zone at Comcast is 5 million DNS records. Records change all the time, and they wanted to be able to throttle updates at a zone level was a requirement that they gave us. And this presented a lot of challenges from an event sourcing standpoint, because you can imagine replaying tens of millions of events takes a long time. And then also holding all that state in memory would just require gobs of memory. So there was fundamental challenges to the architecture that we had started with. And so we decided to take a different approach and rebuild so that we could meet the scale. And so we decided to stay with Akka because it had been so good to us. We want to replace event sourcing with Akka Persistent with our own persistence layer built on DynamoDB. How many people here DynamoDB? Awesome. Cool. We kept with Akka clustering and cluster sharding because it managed the message routing and high availability for us. So that was the approach. And then there's a new word out here, CQRS. That's kind of the architecture pattern. It means an application with eventual consistency, although it sounds a lot fancier to say that. And the idea is that you have your command processing side, and then you have your read side, and then you assume eventual consistency in terms of your state being updated. The nice thing is that we were able to get our zone throttling because, you know, again, message delivery made sure that all messages were delivered to the same zone. So we're able to use that zone actor as a choke point. And then basically just do a wrapper. It's a decorator around, around handling these requests. And this is kind of what it looks like. This is some code for creating our timer throttler. And all you're doing is when you create the timer throttler, you're passing in the actual actor that you want to throttle, and then a rate, which is 5 messages per second in this instance. So pretty easy. And the last thing that we decided to do was actor everything. We really did. The read side, queries, everything were actors. All the command processing were actors. The DNS interface was an actor. And so to recap what we did in the version 2 of the system was HA message delivery largely stayed the same with Akka clustering and cluster sharding. Throttling came out of the box. Again, Akka has lots of tools. We were able to support our new scale. We did have to write a lot more code. I mean, it was the entire persistence layer as well as the command processing. We had to do a lot more heavy lifting than was done with the event sourcing solution. And really we learned that we really should have known this up front. Right? You don't want to be changing your entire application and architecture midstream while the ship is floating in the water. So 2017, we had been in production for over a year. We had a growing customer base and more importantly, a growing code base. And everything was great until it wasn't. So a few issues manifested themselves. One was networking issues and the other one were actor issues. On the networking side, Akka clustering is fantastic at letting you as a programmer not have to worry about anything about the network and the gossip protocol and the failure detectors and things like that. The bad thing about Akka clustering is the network. I like to say the network doesn't like you, and certainly the network doesn't like any distributed system. And so these kind of cropped up, as we'll see now. Recall that our cluster is multiple nodes managed by a gossip protocol. Well, there's this condition. How many people here Akka cluster? Cool. So you know what I'm going to say. All right, called a split brain. And so the split brain scenario is where you can actually, in a network partition or a prolonged network partition, you can kind of form multiple clusters based off the number of machines in your cluster, or a number of machines that are participating in your cluster. And what this means is now I can have my zone represented multiple times in my in real life. And of course, this ruins our SLA because now I get more updates per second than were imagined because I have 2 instances of my zone instead of 1. And then the other thing it does is that we designed the backend processing for idempotency so that you could repeat the same change multiple times, but the same change running at exactly the same time was a little bit hard to figure out, okay? The other problem that we had was with actor issues. The good things about actors is actors bring sanity to the world of concurrency. You can view everything that happens within the receive block as being processed by one thread at a time. It's fantastic. The bad things is that actors are non-deterministic by their nature, and we'll show that in a second. And we started because of all these actors having elements of MOOP creeping its way back into our code base. So to talk about actors, we typically think about invoking methods by invoking behavior by calling methods and getting a request response type of paradigm. But with actors, what we're actually doing is putting a message in a mailbox, and we're just hoping that the actor will actually process it at some point. So it has almost like technically at most once semantics, but maybe once semantics is the way I'd like to talk about it. The other thing is that actors have 2 modes of communication. All of them have tell, which is sending a message, it's fire and forget. And then Akka comes with this pattern called ask, where you send a message to one actor and then you're going to wait a period of time and expecting to get another message back. So what does that look like? How many people here are parents? How many people here have parents? Cool, see, I get everybody. All right. So, I'll kind of show some of the issues that we had. Now, here's Dad, and he has a child. Ryan is one of my children. He is a teenager. And when Dad receives the to-do list from the wife, I might respond to her and say, okay, dear. But when the trash needs to go out, it's not my job. I'm going to go tell my son to take out the trash. Okay. So in this instance, when Ryan gets the message, take out the trash, he's going to respond, well, maybe later. And then my classic dad response in real life is, I wasn't asking you. Okay. All right. But what happens in an actor system is that message never got to Dad because he didn't know how to handle it. It goes in dead letters. Now you can imagine my reaction in the next day when the trash truck is coming down the street and the trash is not by the curb. I never got the message that you said maybe later. One of the other issues is with ask. And so imagine we're eating dinner around the table and I might ask Ryan in this instance, and I say, how was school? And I pipe the response back to yourself. That's the way that actors work. Now Ryan might be on his phone. He might have his favorite Twitch feed starts. And then there's this kind of concept within Akka where you can become an alternative type of behavior. So Ryan becomes watching his phone when his Twitch feed starts. And what happens when Ryan's watching his phone? Nothing, right? Nothing's happening. So in the real world, when I ask Ryan how was school, I get an Akka timeout exception. Right? That was not expected. So the state of affairs in version 2, I'm sorry, this was version 2, is that Akka clustering and cluster sharding gave us HA and message delivery. However, comes along with its split brain and network partitions and some of the ugliness of the network. While actors bring sanity to the world of concurrency, turns out that our system was largely sequential, and actors were kind of overkill for what we're trying to do. And in addition to that, the lack of the determinism made the system over time hard to continue to extend and even understand. And the last point I was taking and reflecting on this was that the persistence layer was getting unwieldy with DynamoDB. You DynamoDB folks can ping me at happy hour. Fun stories. So we decided that we're going to rebuild this again. In 2017, I created the pet store as an example to say, hey, does FP really work in an application environment? And I did find out that FP was indeed the anti-venom to MOOP. And we want to really simplify everything. And the way that we really did this in version 3 was remove Akka clustering, replace actors with functions, and change our database. And the way that we were able to achieve high availability and message delivery was using a message queue. Turns out they're really good at that. Turns out that the SQS is almost free for our workloads. I think we pay like $1 a month. And it does give us at least once message delivery and retries in the event that your node goes down midstream of processing. We are able to still achieve rate limiting using SQS and FS2. I have the naive rate limiting on the side there. But we use FS2 for command processing. And so, because FS2 is just a simpler way to kind of reason about your flows than all these actors that were working in the background. And to give you an example, this is really close to our FS2 implementation that we have in production today. And it just turns out that all these things are just functions. Okay, we pull for a batch of 10 from SQS, we process those changes, and we may delete messages from SQS if there's no errors. Remember our example before using actors, taking out the trash, and Ryan's responding with maybe later. Now with functions, I can certainly predict what Ryan might say by always returning some value that I can handle. He might say, maybe later, unit assumes that he's going to take out the trash as a side effect. And it makes my dad function and my dad life a lot easier as well. You know, if Ryan were to respond negatively, I can respond with, I wasn't asking. Okay. Also remember the receive example. Ryan's watching his Twitch feed and he becomes watching phone and doesn't do anything. Now Ryan has to say, how was school? And actually return a school status. Again, making my job as a dad a lot easier while I'm eating dinner. I can say, Ryan, how was school? And I can say, Ryan, that was great, pal. Okay. And then the final thing is changing the database to MySQL. That was weird. So my badge just fell off. So this is running a query in DynamoDB. So we're trying to get all the records for a zone. And this is kind of what it looks like. And there's the ... actually means that I pull data out, right? It's not meant for anything else. It actually is, there's other content there. But when querying in MySQL, this is what you see. I said before and after. Okay. All right. So, recap. Replace Akka cluster sharding with SQS and FS2. During this time, I eliminated thousands of lines of code. I think it was about 5,000 to 6,000 lines of code. FS2 is more declarative. We are able to do this whole thing in about 3 weeks, believe it or not. And then the other thing about having SQS and FS2 is that we can go active-active, so our HA story is actually better. We replaced actors with functions. That brought back determinism to our system. New features were much easier to implement without breaking everything in strange ways. And changing the database. SQL is easier and much more universal. If anything, everybody that comes out of college knows SQL, which is great. And then also the power of SQL gives us things that are just not possible within DynamoDB, or not easily possible, or inexpensively possible. So, that's my animation. All right, so sometimes, I don't even know how to redo it. So lessons learned overall. Sometimes premature optimization is okay. We really should have asked if this system was suitable for all of Comcast at the beginning, and we would have avoided all of the issues that we had. I would say a lot about the SCALA communities are incredible. The Akka community was fantastic. I forgot to mention the type level community is fantastic as well. I worked a lot with people in Gitter, and they were just awesome in responding to me. It helps that I work with Michael Pilquist as well. That's my cheat sheet. Functional programming does bring the fun back into programming, I like to say. It is the answer to most MOOP issues, so if you're dealing with MOOP, make sure you're looking at functional programming. Actors are great at concurrency. They're not suitable for every application out there. And then the last thing that I learned, I kind of knew, but it's just kind of in hindsight, is that use the right tool for the job. Message queues are great at doing message queue things. NoSQL is out is tongue-in-cheek. NoSQL is out, SQL is back in. But there are workloads appropriate for NoSQL, obviously. But SQL is actually good for even very large data. When you have billions of things, hundreds of millions of things, yeah, look at SQL. It's still a really good thing for doing any kind of data processing. This is my last slide. The system we talked about right now is Vinyl DNS. It's out there in the open. If you're interested in seeing what a code that has evolved multiple times looks like, hopefully there are warts in there, but there's also a fair amount of good in there right now. The SCALA pet store is something that I worked on that I mentioned earlier. You can go out and check it out. Hopefully we'll have a version for SCALA 3 coming up. And the last thing is I work with some people, a second team that I'm really close to, and we're doing, imagine FS2 is declarative programming for stream processing. Imagine being able to do the same things for network functions in Rust, which is actually pretty cool. So that's the link for MB2, and that's my Twitter handle. And that's my talk.
Would you like to take any questions?
Any questions?
A few minutes. We have a few minutes for questions. Great.
Sure.
I'm going to go here just because you're closer.
What solutions did you approach for split brain, and what was the outcome?
So I had to take that out because the time was cut. So what we actually wound up doing was we built our own static quorum-based split brain resolver, which static quorum is basically if there's 3 nodes in a cluster and the number 2 forms a quorum, then if one of the members recognize that there's a cluster event and says, hey, how many people are my cluster, and it's less than quorum, it automatically shuts itself down. So here's the fun part of that story. I appreciate you asking. We run our own private cloud, and can you imagine a scenario where all connectivity is lost between all clusters? What would happen? Everybody shut themselves down. We had a production incident, and that actually was the impetus for version 3. Largely, we just disabled it and crossed our fingers, but that was, we looked at the logs and we were just like, yeah, it was working. It did exactly what it was supposed to be. We lost connectivity between all the nodes in our cluster. It was amazing.
Mm-hmm.
Does that answer your question?
Yeah, and to do this, you had a static number that each node knew, and that was the number of servers you had.
Yep, yeah.
You couldn't change that without letting everybody know the new number.
Yeah, you'd have to do a redeploy updated configuration. It was a static number that you had to know. Yeah.
Yeah, so in your last graph, it looks like you are using the single node FS2 to build the data, and then that we're going to push the result and the DNS records to a lot of the services, and those are just like read-only copy of the DNS records and serve requests. Is that the case?
Is it this one or something else?
This one, yes.
So yeah, the way that we have FS2 running on every single node that's out there, and when a command comes in to one of these nodes, it runs that little FS2 flow, and it will actually issue an update via DDNS to do an update to the DNS backend. So we actually have configured the authoritative masters in our system. So we're actually sending a command saying, create this record in DNS and over DDNS, and it's giving us a response back. Does that answer your question? Okay, thank you.
Would Akka typed have resolved part of the issues?
Yeah, so that's a good point. Again, the setting was 2015, 2016, far before I think even Akka type was, maybe it was in prototype land. But yeah, I think that certainly from a standpoint of determinism, it probably would solve our issues or some of the issues. I haven't looked at Akka type, to be honest with you. If some of the timeout things would happen, how the ASK pattern has evolved and things like that. But certainly, I think if we had something like Akka typed, it would have definitely been easier. Yeah.
And one more.
Okay.
In this graph, you said that the FS2 handler runs basically on every node that you have. So you could have 2 messages for the same record come in on 2 different places. Do you basically use the transactional qualities of MySQL to make sure that your state doesn't get into an inconsistent state?
Yeah, so that's a good question. When you're distributed in an active-active standpoint, at some point you have to figure out, where do you stop? So, every time a request comes in, we interrogate the message and the current state in the database to figure out, hey, can this thing actually happen? Certainly there's race conditions that could go on, and you're going to have that in this architecture. We just more or less accept the fact that somebody could be doing, so in theory you can't be doing a delete before an add, but you could process them out of order in a DNS backend. Truth is, we don't. Most of the same record updating at the same exact time doesn't even really happen. To let you know, scope of our system, we handle probably about 50 to 60,000 updates a week. There's millions of requests across the system, but 50 to 60,000 per week is still pretty small. So the chance of that, what you're happening, we just kind of live with. We have the audit history, so we know it happened, but we haven't seen that in practice. But thank you, it's a good question.
Great. Well, thanks so much, Paul, for that really interesting talk.
Thank you.